recording. Thank you. You must check. You guys can actually see whether I'm recording or not at the top of the screen. Okay. So if we're dealing with an electric field, it's different from an electrostatic force. Electrostatic forces are what we dealt with in the last lesson, where we looked at the fact that you'd use your Coulomb's constant, which is 9 times 10 to the 9, the product of the two charges measured in Coulombs, and the distance between them. Don't forget that's squared. I know I did in one of the examples because I had a squared at the top, and I kind of mentally thought I'd got there. Make sure that you've got all of that. Electric fields are different. And also within electric fields, we're going to be talking about two things which sound the same, but are very different, and you need to differentiate. So I'm going to make it easy by putting both of them next to each other. I hope that doesn't make it harder. If it does, I'm really sorry. We're going to be talking about electric fields, and then the second thing that we're going to talk about is an electric field at a point. When I was at school, we didn't talk about an electric field at a point. We spoke about the electric field strength. So please, you need to know that these are two different concepts. They're linked, but they're different. So an electric field is an area around a charged object where another charged object will experience a force. Please note that these fields, we represent them using imaginary field lines. We try to create field lines to represent the field that's there. But we've already spoken about the fact that if you put a positive charge here, and we then stuck another charge over here, this charge would experience a force due to that charge. And in fact, because this is positive and this is positive, we'll have repulsion, and it'll be repelled. In fact, we call it radially, like as in a radius, radially away. So this charge creates the field, and this little charge experiences the field, and we're going to have a way of drawing what this field looks like. Okay, now I'm pretty sure that Alex is somewhere out there. Alex, I'm giving you a bad analogy warning already. When it comes to electric fields are three-dimensional. The further away a charge is from the positive charge, the weaker the field will be. So the field is strongest closest to the charge and weaker further away from it. It's three-dimensional. I often talk about a body odor sphere. It's a very bad analogy. But around a person, there is an area in which you would smell that person. And the further away you are from them, the less that force of attraction or repulsion would be. The closer you are to them, the more you can smell them and the more you'd be attracted or repelled. It's three-dimensional, but we're not usually above or below each other, so we don't experience that aspect of it. So if you are next to somebody and they smell nice, you might be attracted in. And if they don't smell nice, you might very subtly move your chair across to get away from them. So charges don't really have the sense of smell or anything like that, but it's an area around a charged object in which another charged object would either be attracted or repelled. Further away, the field is weaker. Closer to the object, the field is stronger. And this word here, just being the field, is the area, the region, the space. It's here, okay? That is the field, okay? When we talk about the electric field at a point, we now start talking about how strong the field is, which is linked to how, so it's how strong, sorry, just give me a second, I just got to mute somebody. There we go. How strong the field is. So we then bring in an equation. So the electric field at a point is defined by the equation. So electric field at a point is called the letter E. This is the whole thing. Electric field at a point, the whole thing is E. Electric field is just the area. So an electric field at the point can be worked out using the equation F over Q, where E is, I call it the electric field strength, but you'll find that it comes under the definition of electric field at a point. Okay, so you'll often find that it's not referred to as electric field strength. And this is measured in newtons per coulomb. You can also write it as N/C, nobody will mind. And it is the ratio of the force, which is measured in newtons, divided by the charge, which is measured in coulombs. So this is the formula for it. Please, you'll notice in a matric exam, they always say, define using words. Because if they just said define, you could technically get away with writing down E is F over Q, and you've defined electric field at a point. So the reason they tell you specifically you have to use the words is your electric field at a point. Please, you'd have to write this line down before you carried on with what I'm writing below. So the electric field at a point is the force per unit of positive charge, or the force experienced. You can put in other words here, but the idea is it's a force per unit of positive charge experienced at that point in a field. The key idea here is force per unit of charge, with me underlining the word positive about 4 times. The reason you have to identify positive is whenever we decide which way we're going to define a field, we do it according to a positive charge. I always have students in grade 11 who go, but how do you know the direction? The direction is the direction in which a positive charge would move if it were placed at that point. We specifically use the terminology that it is a positive point charge. And the idea of a point charge is that it's imaginary. It doesn't really exist. Because it's imaginary, it's just a positive. It has no mass, it has no volume, it has no physical properties other than that it's a positive and that it's there. So we imagine, I have this little picture in my head that it's just a little plus that's there. And it behaves as a plus would behave if it didn't have to worry about gravity or any other forces acting on it. So we're going to be using electric fields and discussing how electric fields work. That is our big focus for today. But it's electric fields, and the electric field's the area. Electric field at a point, or electric field strength, is how strong the force is. Now, the reason that we focus not just on how big the force is, but the electric field strength, is something that's a bigger charge will experience a bigger force. And that won't necessarily tell us that we've got a stronger field, because we could change how big the charge is that we put at a specific point. Whereas your electric field strength, your E value, is going to be a constant, and depending on how the charge changes, the force will change. So you can work out how big a force any charge would experience if it were placed at that particular point. All right, I know I'm recording this, but I don't think everybody that's here is likely to go back and watch it again. So I'm going to suggest you quickly take a screenshot if you'd like to, before I move on to the field diagrams. Okay, all right, so I'm going to quickly just clear my board, and then I'm going to take a second. Can I quickly check in with everybody? Everybody good with what I've said so far? Give me a thumbs up if you're on the same page. Okay, good. I'm seeing quite a few thumbs up, so that's perfect. All right. Okay, cool. I'm also just quickly scouring through and seeing if I can find the people that I'm looking for that are hopefully attending tonight. All right, let me just quickly check. Is this call being recorded? We did that. What was the NC? Sorry, Zev, we're going to get back to that in a second. It's the units of electric field strength. It's force divided by charge, so it's units on newtons per coulomb. So hence the N/C, or the NC to the -1. Remember, both of them are uppercase, but I see you got that, so it isn't an issue. That's just me adding in. All right, let's go back. Okay, so we're going to often be asked to draw the diagram around a charged object. So I'm going to start off by drawing, in fact, I'm going to do them one at a time. I normally draw them next to each other, but people might get confused. So we're going to do one, then I'm going to clear it, then I'm going to do another, just that we don't mess up with anyone getting confused. If I put a charged object, sorry, if I'm drawing the electric field around this positive charge, and I put a point charge there, it's a positive point charge. 2 positives will repel, so this charge would want to move away from the positive. So when we draw this pattern, this is the electric field pattern around a positive point charge. I always find that I draw 8 lines because it's easy. And I always start with the horizontal vertical and then add in my diagonals. So that over there represents the electric field. So this over here is the diagram for the electric field around a single or an isolated positive charge. Okay, and we must remember that the direction of the field always points in the direction that a positive charge will move. So it's away from a positive and towards a negative. We'll cover the towards a negative just now. There are a couple of rules for electric field lines. Okay, electric field lines, first of all, are imaginary. You can't see them. That means that if I were to go and take something, rub it against my hair, and now everything's charged, I can't see these magical field lines all over the place. They're completely hypothetical, and we use them as a model to imagine what's happening. Okay. The second thing is that the field lines must enter or exit all objects at 90 degrees to the surface. And very importantly, this is where some of you guys are terrible with your drawings, is that some of you guys go, oh, cool, look, no, but I did it. Look, there we go. I messed up on that line. I'll get rid of it just now. You look at it and you're like, yeah, no, cool, got 4 marks. I hate to tell you, you didn't get a single mark for that. You might if you've got a very lenient teacher or examiner, depending on, well, you wouldn't get a specific examiner who's more or less lenient. They have very strict rules. So everybody has to mark the same way. But you might get a direction mark there if it's worth 2 marks. If it's just 1 mark, you've got a problem because your field lines have to touch. I'd recommend you even draw this if you can and you're in an exam drawing with a ruler. So ideally, when I'm getting pedantic, I even draw in my little 90 degrees to say, look, it's perfect. And I make sure that they touch. Every one of these must touch, but not pass through. So please, once again, if you've got a positive and these lines go through, it's wrong, okay? I'd almost recommend that if your lines do this, that you get an eraser and you neaten them up, okay? So once again, all of the ones I'm getting rid of are not what you want to do, okay? The one that I've got there is good. You don't have to show that it's 90 degrees, but it's one of those show-off things that some of us do, okay? So the field lines are imaginary. The field lines must exit and enter all objects at perpendicular or 90 degrees to the surface. You'll see when we're doing 2 charges just now why that's so important. And then this isn't really a rule about it, but it's a point. The density or closeness of the field lines indicates the strength of the magnetic, of the electric field. Can't swap my fields here. Okay, so your electric field at a point is indicated by the strength of, or by the density of the lines. So closer together or closer to the charge, you'll see that these lines are closer together. Over here, further away, they're further apart. Okay, so further away from the charge, they're further apart. Okay. I hope everybody's good with that. Quickly take your screenshots now so that I can carry on with the next one. All right. The next one is if we look at a negative charge. Oh, let's do a negative. If we did a negative charge and I put a positive here, you can always just imagine. Say to yourself, I put a positive there, which way does it go? Some of you can do this off by heart. Some of you need these guidelines. So here, with a negative, everything moves inwards. Sometimes it's a little bit tricky, I'm just being honest here, to draw all of these arrows. So many of your teachers, this is just how I've always drawn it, don't go too far in. Some of your teachers may instead suggest that you draw all of the lines, and then you are allowed to draw the arrows on the lines like that. So both of those are perfectly acceptable. This one looks a little bit more like a snowflake, but the point is that both of those are acceptable, okay? So electric field lines are away from a positive towards a negative, and that is specifically because they show the direction which a positive point charge would move. So this over here is the electric field around an isolated negative charge. Isolated, single, those are the words that they use. So they may ask you to draw an electric field around just the one charge or just the other charge. So charge P or Q, told you they use P and Q, or they may ask you to draw a field around two charges. We usually don't do more than two. So I'm just quickly going to show you how to do two. If you've got a positive and a negative, it's rather easy. The electric field is usually going to be radial, very close to its own charge and move further apart. So here we're going to show that a positive point charge moves directly, or the field line, the positive point charge would go directly away from here and towards here. Now the rule of the 90 degrees comes in. This leaves here and then bends around in order to enter here at 90. Do your best to make it look like it's at 90. It's very difficult sometimes, but that's why we get the arcing or the bending. Also do your best to make sure that it touches. I find that once I've drawn about 4 or 5 of them that look right, ideally 5 because one goes that way and then 2 on each side makes it even. You then just go up, diagonal, back, diagonal, down. Yes, MZ? Okay, no MZ. All right. Everybody happy with that? So the field lines, remember, always go from positive, away from positive, and in towards negative. Okay. So that is the electric field between a positive and a negative object. If, I'm going to just quickly see if I can do this. If we flip the two around, oh, let's see if I know I can't. Okay, let's try again. There we go. Yeah, I did it. Okay. If we flip the charges and swap where the positive and negative is, that's what it'll look like. Okay, so please just always bear in mind we can make them this way or any direction we want to. You've still got to be able to work with them. All right, I'm going to quickly clear all the drawings here. I'm going to show you the last type of charge. Okay, Tristan, I'm not certain if you've got a question. If you do, you must quickly speak up. So if I do the electric field...
Those lines at the back.
Yes?
The lines at the back, could they be curved or do they have to be straight?
Which ones? Yeah.
The lines that are not connected with, yeah, those back ones. Is it wrong if they're curved?
Do you know what? It's one of those where different teachers' textbooks, resources will tell you different things. Realistically, these two charges will interfere with each other in all sorts of ways. So what's actually happening is this one will go, can you see my picture? Yeah, you can. Go all the way around to there. This one will go all the way around the world. So to the end of my page, around the world, and then back, oh gosh, let's move that back in on the other side of the world. Okay, so it's going all the way around the world. So if you curve these just a little bit, we usually don't freak out. And I can tell you with certainty, I've definitely seen textbooks where they curve them. So I tend to teach this with the exiting and entering at 90. And when it gets to the edges and it gets complicated, I ignore it. It's not something, however, that you're going to get penalized on. Does that make sense? So if you curve them a bit, it's not going to be the end of the world, but I tend to like to do it this way. So I'm very much a creature of habit in terms of why I do it certain ways, but I do appreciate that certain textbooks, I've definitely seen versions where I download them from the internet and then have to sit there going, yeah, I'll just stick it in anyway, it's close enough. All right. If we did between, or the electric field between...
Perfect, thank
pleasure.
you.
Between two negatively charged objects, electric fields show the direction in which a positive moves, so it would move away. Now, I find when I draw them and they're both the same charge, I use a rule. I never send out one, I send out two because they're going to split. And if you've only got one, you're going to find it very hard to split it. I here always will send out two, ooh, not quite that messily, send out two and then split them. Where you split them doesn't really matter. Some people split them from right at the beginning. Some people split them later. It doesn't really matter. I usually curve maybe the first two that come out. All of this is very kind of, if you're close enough, you get the marks. And then, as you know, I really like to just make this nice and easy. All of my lines around the back, quick, done. All right, so that is two negative point charges. And if we did the same thing with two positive point charges, it would be exactly the same, except that now the positive point charge, sorry, two positive isolated charges, the point charges would come in along the same pattern. So it would be exactly like this, except that the arrows would point inwards. So I'm going to do this over here. Sorry, they should never touch. Another rule about electric field lines. They never touch, they never cross. Okay, so I'm just quickly going to draw the general pattern. You'll see it's exactly the same as the one above. Please make yours a little bit neater. I'm just doing this very quickly, and I'm not going to use my ruler because it takes too long. So here, these all come inwards. Okay. I also mentioned to you that the strength of the electric field is shown by the density of the lines, which realistically means that if one of them has got a larger charge, you could, but don't have to for marks, put more field lines in. Okay, so if you're being 100% correct, that's what you should do. Oh, damn, thank you. See, I'm very special at this. Thank you very much, Kim. I've done my arrows the wrong way. If we put a positive point charge here, it would come inwards. It's one of my special things that I do. So let me just quickly go in here. And erase and change everything. Okay, everybody, everything that you've just heard is wrong, except I'm going to do this a really quick and easy way. Thank you, Kim, for watching what I was doing. So if field lines go away from the positive, wait, have I done that wrong again? No, that is right. And in towards a negative. So I apologize. I've done it perfectly incorrectly. There you go. That's now the correct version. Okay. I worried initially when I was doing these that if I make a mistake, people panic. But I've actually been told that it keeps you guys more engaged when I make a mistake. Because then you suddenly go, oh, wait, what did she do? Okay, let's get off my phone and start paying attention again. So I'm okay with making mistakes. I do apologize. I do make them occasionally, but I try not to. Hopefully it doesn't detract from anything. All right. Everybody happy with the field diagrams and how they look? Yes? Okay, so just give me a second. I'm going to stop sharing so that I can actually see the people. Everybody happy with that? Yay. Okay, I've got some hands up here. Most of you are still good. Cool. Brilliant. And I see Chris is also here. Yay, I found him. Okay, let's keep going. So continuing onwards, we're now going to move on to the two equations that we use. Hopefully from the last lesson, you'll have remembered Coulomb's law, which is F is K, Q1 plus Q2 over R squared. We're not going to be using that, in fact, to prove my additional equation that I'm coming up with. I'd like it very much if all of you use Siavula to do extra practice, because there isn't enough time, even if we're using the full 2.5 hours each week, there's not always going to be enough time for me to rigorously test you. Whereas if you take what you've learned here, go and practice it there, that'll give you an opportunity to kind of fill in the blanks that I can't fill in. Siavula also gives you fantastic solutions for once you've got it wrong, how to go back in, correct it, etc. There's also one really clever thing with Siavula, and you can try it out if you get there. If you find a question where you think their answer is wrong and you're adamant yours is right, you can actually send me and just tell me that it was one of the questions you struggled with, and I have the ability to go and check the exact version of each question that you've answered. I haven't yet tried to do it, but I believe I can, and I was shown how, so I will be able to get there. So the two equations we've done so far is that the electric field strength is the force per unit charge, and the fact that according to Coulomb's law, that the force is equal to K Q1 Q2 over R squared. Okay, remember that K is 9 times 10 to the 9. I did show you where you could get it. I know that there are a whole bunch more units here, but we're not going to be using them because they aren't important. So, quick refresher. Electric field strength or electric field at a point measured in newtons per coulomb. Force measured in newtons, charge measured in coulombs. Coulombs constant. Charge measured in coulombs, charge measured in coulombs, distance measured in meters. Please make sure that you remember all of those quantities or those units. If you don't have them in the right units, your answers are not going to be correct. And last and very important, even for me to remember, don't forget that squared. Okay, so what we're now going to be doing is we're going to quickly come up with a different equation to work out the electric field strength. And that is going to be by combining these two, because this force and this force are exactly the same thing. I'm also going to show you that this is where in the previous lesson I told you Q can be an upper or a lower case. Now I'm going to show you why I personally use one as an upper and one as a lowercase. So I regard big fat Q as being the big bully that's creating a field, and little q as being the charge that's experiencing a field. Please note, technically, this charge is also creating a field that the big charge is experiencing. It's just my perspective where I'm choosing to make one experiencing and one creating. When we use this equation, this q here must be the charge that experiences the field. Which means that according to what I've said here, this should actually be our little q. Yes, Hannah, what's your question? Okay, Hannah, you're going to either have to unmute yourself and speak, or you're going to have to type so that I can answer it. All right. I don't know if everybody's aware of it, but if you need to ask a question at any point, you either shout out or you go into participants, find your name and raise your hand. You've got to go in through participants though. Okay, don't worry, it happens. So it was a mistake, don't worry. Okay, so this is the Q that experiences the field. So if I now go in here, I also change this around and I say, you know what? There are two charges, one creates one's experience, so let's call it a big Q and a little q. Now we're going to go and equate these two, but I'm going to start off by saying that E is, sorry, wrong way around, rearrange the equation, that F is equal to E times Q. Now I'm going to do a simultaneous equation where this F equals this F. So I'm going to say that EQ is equal to KQQ over R squared. Because this Q is the same here and here, I can cancel it, which means I get a new equation where E is equal to KQ over R squared. That means that we can define the electric field by the force that the charge experiencing the field has, or by how far away we are from a charge creating a field. So we either need to know this, so this Q and this R to know what the field is at that point, or we need to know what this Q is and what force it experiences. Either what I've written there in blue or in red, we'll be able to calculate the electric field at a point. And quite often we do a sneaky thing where we make you work out using one of the two methods, and then we make you apply the same value, because E will be the same regardless of whether it's this equation or this equation. The electric field at a point is that value at that point. And because we've got these two equations, we can make you work out the question using one and then solve the question using another. Okay, so just quickly, because I've already expanded on what all of these are, E is the electric field strength or electric field at a point. That's very bad. That's the word strength. This is our Coulomb's constant, which is 9 times 10 to the 9. Q is the charge, which must be in coulombs. If you remember right at the beginning of the last lesson, I expressed to you that you could get millicoulombs, microcoulombs, nanocoulombs, or picocoulombs. If you've been given any of those, you'd need to convert it first. And this is the distance away from the charge creating the field. Now, this is where we've got to get very particular. In order for me to work out the electric field at a point, I don't really even need a charge to be there. I can talk about what is the electric field strength or the electric field at a point at this point without me putting a charge there to experience it. Because in order to use this equation, I care about what Q is and I care about what R is. I don't care about what's there. Okay, so we don't actually have to put anything there. And this is where a lot of students get very confused with this section. You'll be given a number of charges and then you'll be told at point X, what happens? And everyone's sitting there going, what's the charge at point X? You don't need to know the charge at point X because you're going to be using this equation. This equation doesn't care about the charge at point X. It cares about the charge creating the field and how far away you are from that point. All right. So at this point, believe it or not, we've covered all of the theory. However, we've applied very little of it. So what I'm going to do for the remaining, how long are we got? Remaining about 20 minutes, is that I'm going to be going through specific examples where we can practice this and see how we put it into practice, okay? We're not necessarily going to get through the hardest kinds, but if I can get you to the point where you can do some basic ones, then you can slowly but surely work on adding on skills and hopefully get to the point where you can do the more tricky questions. All right, I'm going to clear all drawings. I'm going to quickly stop sharing, and then I need to just quickly find, I had a diagram that I wanted to work through with you, but it's a little bit little, so I'm going to hope that everybody's able to see it. Okay, so I need to go back. I know I'm not sharing, don't worry. Okay, so I'm going to quickly share my screen with you. All right. Okay, I know that's very small, but can everybody read the question? Just quickly, I can't see anybody. Let me just quickly check. Anyone, can anyone read that question? Is that writing way too small? Okay, thank you, David. David can read the question. So I'm just going to move this out the way so that I can write and you can still see. Okay, so the question here says, we're going to be using the equation E is equal to F over Q. They've been kind enough to tell us that. And it says, if the magnitude of the electric field, that means this value, is 3 times 10 to the 6 newtons per coulomb at a point, calculate the force acting on a charge. Oh, this is a big question. So we're asked to, no, I lie. I was getting confused there. This isn't a big question. We were asked to calculate the force. I thought they were mixing things up here. To calculate the force acting on a charge, there's the charge. We've been given of -7 nanocoulombs. Now, please, you were asked the word magnitude of the force. If they didn't say magnitude and they just said calculate the force, you'd have to bear in mind that that negative would be a negative charge, and a negative charge would experience a force of attraction. Because, sorry, I've just got to think here. My brain's just gone fritzy. If it's negative, you'd assume that, no, you don't know which way around it is because you don't know what the charge is. Okay, so we don't know which way around it is. But just bear in mind that if we did know that the charge creating the field had a specific charge, you'd have to work out if it was attraction or repulsion. Okay, centering myself and going back to this. So if we go and plug everything in here, we're going to say 3 times 10 to the 6 is equal to the force divided by the charge. Now, the biggest mistake that people are likely to make here is forgetting the nano. So you've got to change that into 7 times 10 to the -9. Please also remember, and I was very specific about this last time, we do not put in a negative with either Q or little e, which is the charge on an electron. Those do not get a negative sign. They are always put in as a positive, and afterwards you pick your direction based on which way around it goes. So here, if we want to rearrange this, the denominator has to get multiplied up. So our force is going to be 3 times 10 to the 6. Yeah, that is correct. Multiplied by 7 times 10 to the -9. And if we do that, 3 times 10 to the 6 multiplied by 7 times 10 to the -9, we get an answer that our force is 0,021 newtons. Okay. So we knew that the electric field was a certain value. They didn't tell us which way the electric field was and whether it was away or towards. Because they said magnitude, we can just get away with writing the answer down like that. Okay. I hope that that makes sense to everybody. Okay, so I'm going to quickly, in fact, I can just change to a new share. I'm not going to do a new share and go back to my whiteboard because I haven't actually prepared another one on that particular section, that particular question. If I instead did a different question where I asked you to calculate the electric field at point X. Okay, so this is our electric field at a point. And I told you, sorry, I just quickly got to check. Can we leave it in scientific form? Always. So scientific notation is always allowed provided that it's the same answer. I just happened on my calculator to get that answer and I decided I was sticking with it. So as long as answers are equivalent, you're fine. Also, when it comes to rounding, there's an unusual assumption that's made by the markers, and that's that nobody in this country knows how to use a memory function and nobody in this country knows how to, so you can't use any memory functions, and that you round up at every single stage. So if you round, as long as you don't round to more than 2 decimal places through all of your working out, you will still get full marks. Okay, so you don't actually have to worry about, oh my gosh, I rounded up a little bit too early, or is my rounding exactly right? They mark you just as much if you round or if you don't round, but you've got to make sure that your final answer has 2 decimal places. They accept a small range of answers because they know that some students, I'm one of them, I will keep every single value in my calculator. I will not lose a single one of them because I like to get exact answers. And my answers are in fact often not the exact same ones that are in the memo, because the memos are worked out by rounding at every single step. So every single time you get to a value that you're going to plug in the next step, they round it to 2 decimal places and then keep going. So you can do either. So we're asked to work out the electric field at point X. So imagine over here, I have got this charge. Okay, let's make it a positive charge. I could even call it P. And this is going to be a charge of 7 millicoulombs. And I want to know point X. I've just told you don't have to make that an arrow. I probably shouldn't. Okay, if we've got point X over here, you're asked to work out the electric field at point X. Now, because we've been given the charge creating the field and the distance away, we should, from this, use the equation that electric field strength is equal to KQ over R squared. That would be our choice of equation because of what we've got. Our value of K is 9 times 10 to the 9. The value of Q is 7 millicoulombs. Please don't forget that milli is times 10 to the negative 3. This, getting confused between what your units are, is one of the biggest places where people have an issue. I completely forgot to tell you what R was. You need to either know one of those two. So let me just quickly stick in here that that's 10 centimeters. The problem when your teacher makes up questions as she goes. This has to be in meters. So it's 0.1 meters. So that's going to be 0.1 squared. And if I work that out, I'm sure some of you have already beaten me to an answer, though some of you did get delayed because I hadn't given you enough information. Sorry, I was worried I entered something twice there. I get an answer and it's very big. Okay, so this is 6, so let's count my zeros, 3, 6, so it's going to be 6,3 times 10 to the power of 9 newtons per coulomb. Electric field strengths tend to be very big values, so please don't panic if you end up with a very big value. It's not necessarily going to be a sign that you've messed up or that you've got something wrong. It's just that you need to kind of bring all of those pieces together. Okay. So at this point, I have shown you every one of the equations in a very simple way to do every one of the questions. However, we haven't even started dealing with the very tricky things. So what I think I'd like to do, and I know I'm probably going to scare some people, but I think we need to just deal with a trickier question. I'm going to ask us, if everyone's prepared to do this, to do a question where we work out the net electric field strength at a point. Okay, so at this point, I would strongly suggest breathe in, breathe out. Let's do this. Okay, so I'm going to clear all my drawings off. All right, I'm not going to pick on any particular past paper question. I'm going to quickly make up one, and I'm hopefully going to give you all the information you need. So I'm going to call this point P, and I'm going to, well, charge P, and I'm going to give it a value of negative 3 millicoulombs. I'm going to do charge Q. Okay, I'm going to tell you that these two, I'm giving the values. Please, when I say these two, I mean from the center of here to the center here. It's exactly that distance. I'm just drawing a really rough sketch, so it's not going to be in there. I'm going to tell you that that is 2 centimeters, 12 centimeters, changed my mind. Okay, let's just quickly erase those. They're going to distract me. And then Q has a charge of minus 5 millicoulombs. Sorry, just quickly checking. Is that positive 3 millicoulombs? Yes, Brannon, it is. All right. So we've got positive 3, negative 5. These are both charges. I tend, when I draw my pictures, to make charges colored in dots or dots, and points are labeled with a cross. And my question here to you is going to be, here's point X. I'll even label it. And point X is going to be 5 centimeters beyond those. And I would like, as a question, to ask you to please calculate the electric field or electric field strength at point X. So this might, for some of you, be a little bit of a challenging question. Please don't panic if it's a little bit of a challenging question. These are the kind of questions you're actually going to get. Okay, so what I always find helps me personally here is I draw a diagram. A little bit like you guys would have been used to drawing force diagrams, except I'm going to draw an electric field strength diagram. So I'm going to go and imagine at point X that here's the object. And you can either view this in terms of being the force that it experiences or the electric field strength. Because remember, your electric field is going to be your force per unit charge. Okay, so if it's experiencing a force in a specific direction, it would also have a field at, well, it would link to the same direction. So remember that this position X, we imagine we put a positive point charge there. So if you're confused about which direction things are going to act at, X is not a charge, but what is at X is positive, always. So if we look at P, if this is positive and this is positive, it would be repelled away from P. So the electric field strength due to P is going to be towards the right. That's my direction. Okay? And the strength of that electric field, I can work out. I'm going to do this slowly in parts. You can always bring them all together, but I'm going to break it down so that you've got an easy segmented way to deal with it. The electric field strength at P, you don't have to put in a subscript if you don't want to. That's just for me to remind myself that I'm talking about P and not Q. I'm going to make Q red just now so we can see it's different. The electric field strength is going to be KQ over R squared. If we want, we can even put in subscripts here to show which things we're talking about. You don't have to. So my K value is 9 times 10 to the 9. The Q value that I've got here is 3 millicoulombs, which is 10 to the negative 3. Don't forget that. Then comes the distance, and this is where people get silly. We need the distance from P to X. Not from Q to X or from P to Q, from P to X. P to X is 12 centimeters plus 5 centimeters, so it's 17 centimeters. Except we can't write 17 because that's in centimeters. We need to divide it by 100 to get 0.17 meters. And then we mustn't forget to square it. So this will be 9 times 10 to the 9 times 3 times 10 to the negative 3. Be very careful here when you divide. You're going to have to divide and you're going to have to make good use of your brackets as well so that you don't end up dividing by this and then squaring the whole thing. So please just be aware of that. I get an electric field strength that is a horrible number. So 934256055,4. I leave it all in and I write newtons per coulomb. And then I remind myself that if there was a positive place at point X, remember X is not a charge, it's just a point, that the electric field at that strength, the electric field and the strength at that point would be away from P. So I'm going to say here to the right. Then I'm going to repeat this exact activity for Q. Q is negative, so if I put a positive charge here, it would be attracted. It is not beyond the allowances that you will have both of these being positive, and when you draw your little diagrams, you'll actually have both of your electric fields going in one direction. That's allowed, okay? In fact, we can even give you examples where there's more than two, but then it involves you doing weird things. Let's just get my writing right here. Good, there we go, to the right. Okay, carrying on. I'm not going to work out the electric field due to Q. So the electric field due to charge Q is going to be KQ over R squared. Once again, if you wish, you could put in subscript Q there and there, but I find as long as I've got it here, I remember which one I'm dealing with. 9 times 10 to the 9, that's a constant. Charge Q is now different. It's going to be 5 times 10 to the negative 3. Remember, We don't put in the negative. The negative is already determined that this is going to go to the left. Okay, so that's where the negative comes in. The distance r is between q and x. Okay, got a question? Is that the direction that p or x would move? It's actually neither. That is the direction of the electric fields that, well, the electric field at point x. It's not charge x. X is a point. It's just a position in space. So if I imagine that I had a charge here, the point would be there. And it's just where it is. There isn't anything that's actually there. It's just a certain position that's a certain distance away. And in fact, rather crazily, if this is 2 centimeters, there'd be another point here that had exactly the same electric field strength if it's also 2 centimeters away. We'd end up with an entire ring of points that all had exactly the same electric field strength, because if we put a charge at point X, and if that charge had a charge of exactly 1 coulomb and it was positive, it would experience this force here due to P, and whatever the force is here that I'm going to get due to Q, it would experience that force in newtons in a particular direction. But X here is just a random position. There's actually nothing there, which is why I drew it with a cross, not with a dot. It's a position. Okay, a little bit like I could go and say there's a position 2 meters in front of me. That's where X is. It's 2 meters in front of me. There's nothing there, but it's, I could say, how bad do I smell 2 meters in front of me? Okay, so using the body odor sphere, that's what is the force at that point, however far away from the thing creating the field. Okay, hopefully I didn't lose you there. The distance between point X, where we were determining the electric field strength, and Q, which is creating it, is 5 centimeters. Remember, when we did from P to X, we had to add them together. Here it's just from Q to X. So this is going to be 5 centimeters, so divided by 100. So 0,05, we square it. And from that, we get 9 times 10 to the 9 times 5 times 10 to the negative 3 divided by 0.05 squared gives me an answer of 1,8 times 10 to the 10 newtons per coulomb. And remember, since this was a negative charge, if we put our hypothetical, it doesn't really exist, but we're talking about it as if it did, positive point charge there, it would experience that force as an attraction. So therefore, this would be to the left. Okay. So I find that I do all of this most of the time. Sometimes I do it a bit shorter or quicker, but this is how you lay it out if you don't want to risk losing track of where things are. So I'm now going to go and use this diagram to work out the net electric field. So I've got a value of big numbers, 934256055,4 newtons per coulomb to the right. And I've got another one of 1,8 times 10 to the 10 newtons per coulomb to the left. Okay, so I've got a question here just quickly, and I'm going to touch on these because I think this is where a lot of people lose things. So I'd rather pause. If we go over time, I presume none of you are going to turn into pumpkins at 8. So I may just go a little bit over time so that we get this done. So the question from Gabriella is, she doesn't understand why it is left or right. Okay, this is where people always get muddled. So I'm going to quickly pause so that we can go back and make sure you've got it. Gabriella, can I ask, do you have a camera and a microphone that works? Just quickly.
Yes.
Okay, brilliant. Yay, hello. Okay, so do you understand? Now keep it on you. Well, I guess it's going to flick back to you every time you speak. So you've got point X here. Do you understand that X is a position? It's not a charge.
Yes.
Okay. Do you understand that when we determine the direction of an electric field, we determine everything according to how a positive point charge would behave? That's even part of our definition of an electric field at a point. It is the force per unit positive charge placed at that point. Does that make sense?
Yeah.
Okay, good. So do you understand that we're not saying that there is a positive here, but we're saying we define everything according to the positive that we're imagining is there. P is positive. So if we're only looking at P, what are these two positives going to do to each other? Attract or repel?
Repel.
Which means that this imaginary point charge here would experience a force, because electric field strength is force per unit charge, it would experience a force of repulsion from P. If it's repelled from P, it will move towards the right.
Okay.
If, on the other hand, remember it's still positive, our allocation of the direction of the electric field being the direction that a positive would move it's an absolute. It's everybody goes the same way, so we don't have half of the people getting it right sometimes and others. It's the direction of an electric field is always the direction in which a positive would move. That is our definition of it. So if this charge here, which by definition has to be positive to show the direction, is placed here, what would it experience when it comes to the negative charge?
It will attract. So then,
Attract. So therefore it would be towards the left.
Yeah.
Does that make sense?
yeah,
So
it
you've
does.
got to
Thank you.
sit and every single time say to yourself, the charge that's at point X is positive. Okay? Don't sit there and go, oh, that didn't tell me whether it was positive or negative. By definition, it's positive. That's how we define electric fields. So that's why we always choose to make it positive and why it's always going to be positive. Okay. All right. Yes, I just had a comment from Luke saying Fisher could represent. I hate to say there are probably more Fisher kids here than most other schools, but they're quite a large number from a large number of different schools. So I don't actually know if Fisher's right there. All right, but we're not going to get into that because I want to keep going with what we're doing. All right. Okay. And then let's continue here. Please, can I ask only important things on the chat? I do check it every time. If you're busy putting other things up there, it distracts. So if I want to work out the net electric field, it is going to, just like net charges, be the sums of the two fields. So it's the sum of the electric field due to P plus the electric field due to Q. And I'm sure you can imagine if you got something like this in a Newton's law question, your rule is pick a direction as positive and stick with it. I just quickly need to count my numbers here. So this will only be times 10 to the 9. So I think this guy's bigger. It's a long day, so I may be wrong. But in order to get this right, I'm going to make this direction positive. Please note here, don't put in a negative sign there. Until we put values in, while they're still variables, we have to algebraically add them. If we add them and they're negative, yes, it is a subtraction, but we don't put negatives in here. It's a bad scientific thing to put a negative there. So I'm going to say my electric field due to P. So I'm actually just going to go with these. I'm going to say P. Oh, I've got them the wrong way around. All right, let's go. So we're going to start with P, which is towards the right. So it's going to be negative 9, 3, 4, 2, 5, 6, 0, 5, 5, 4. And then in the other direction, this is going to be towards the left. So it makes it positive 1, 8 times 10 to the 10. Doesn't actually matter which one you call positive. You should find overall your answer will be a resultant towards the left. So I'm going to take, I've in fact got this still in my calculator. So I'm just going to minus 9, 3, 4, 2, 5, 6. I sound like a politician. 0, 5, 5. Ooh, 0, 5, 5, 4. Let's try and get the calculator right. And I get an answer, it's a very big one, of 1,77065. 7 times 10 to the 10 newtons per coulomb. And since we know this is bigger, it would be to the left or left. If you wish, you can take this to just 2 decimal places. But if you'll remember, I mentioned to you that it's a minimum of 2 decimal places, which means that if you put in more, it's not the end of the world. Okay, so this question here is what you're realistically going to be getting in an exam. Not only are you going to be getting these, but you're going to be getting some tricky ones where instead of doing this, what they can do is they can tell you this distance. So from here to here, and then you've got to guess that this one, maybe if we were told that this was 100 centimeters, you'd have to say, well, this is 100 centimeters and this distance is X. And then you've got to put in variables and say this is 100 minus X. And there's so much that they can do with regards to you having to work out distances or sizes of charges or net electric fields. But the point is that now that you've got the basics, you can go in, use Siavula, practice, If you hit problems that you can't do, send me a message and we'll work through them so we can make sure that we can get to a point where you not only understand the basic theory, but you can apply it. Okay, so I'm going to quickly stop sharing here because we're a little bit over our time. And I just quickly wanted to finish off. Okay, there's a question here from Sarah. Do you take the bigger number as positive direction? I do that for anything because I want a big value minus a smaller value. It's just a personal choice. If you do it the other way around, you end up with a negative answer. And then you just go, well, I said positives this way, so negative must be the other way. It's not the end of the world if you flip it around, as long as you're consistent with your directions being one way or the other. Okay, so I just quickly wanted to make sure that everybody's on the same page as me with regards to what we're doing going further. I'm going to have a look. I know we've still had a couple of people join in over the last day. I'm going to go back and have a look at which sections people have earmarked as being problems. And then I'll let you guys know on the WhatsApp group within the course of the next week exactly which section we're doing next. But going forward, I'm going to be seeing you every Tuesday. I'm here. If you're not here, you miss out, but I'm going to be here. I commit from now till September, every Tuesday from 7 until 8:30, and every Thursday from 7 till 8. The idea, as I've mentioned before, is to cover all of the theory if we can on the Tuesday, and then do practice and hard examples on the Thursday. So you, in fact, between the Tuesday and the Thursday can practice on your own and maybe even come up with specific questions you want me to cover. So that's kind of the idea of where we're going to. The other thing that I did launch, thanks, I can't even remember who it was, to their suggestion about a prize, is I know that there's some people here where sorry, just wait, I'm going to quickly mute again. Okay. I know that there are some people here who are possibly a little bit ahead of the pace at which I'm going. So the idea was that anyone who really shows good mastery on the Siavula website, or who has practiced a lot. So even if you've done lots of examples and you're just not getting them right, but please, you can't just click, click, click. You'll be invited, but it's going to be something done off group. I'll just send a message on the WhatsApp group or contact you individually, and I'll do a small little class with those people, but I will just discuss it when we got the group together, record it and put that up as well. But that's just a little advanced thing for anybody who really wants to stretch themselves. What we're doing here should get the majority of you through. The idea is that extra thing is for people who want to get 80s and 80s, 90s upwards. Okay, all right. Does anybody have any last questions before we finish today? Okay, I've got just one last question. I actually am going to stop recording.